Previously, we added a mechanism that adjusts the difficulty of each new block in order to control how quickly blocks are added to the chain. Primarily, we control the difficulty with an adjust difficulty function, with two parameters, the last block and the current time timestamp. The difficulty increases if the function receives a last block whose timestamp plus a mine rate is greater than the current time received, and in this case, the block was mined too quickly. On the other hand, if the function receives a last block whose timestamp plus a mine rate is lower than the current time received, then the function lowers the difficulty. In this case, the block was mined too slowly. Let's actually test that the difficulty was lowered first within our block.test.js file. So we're going to have a new it function for a unit test that says it lowers the difficulty for slowly mined blocks. And then we have our callback function as the second parameter of this it function. In this test, we'll use our adjust difficulty function with our fresh block instance as the input. And then we'll give our block as an input to adjust difficulty. We'll give a timestamp that is huge, like the current timestamp plus 360,000 milliseconds, which is a whole hour. And for a slowly mined block, we'll expect that the block's difficulty is lowered by 1. So in the body of the function, let's have the expect. The input will be block.adjust difficulty. We'll give it our block, and then the block.timestamp plus that absurdly high value of plus 360,000, which is a whole hour. And then we'll expect this to return a number which is equal to the current block difficulty minus 1, since the difficulty will now be lowered. As we save this, let's test our new addition in the command line now with npm run test. And as we do so, Jest executes, and then it finds the current test, and it actually passes this current test. Except right now, we're getting an error over here for the generate a hash function test. So what we have to do is that we have to adjust this current test that is generating the hash that matches the difficulty. Because when we call mine block within our before each function over here, it actually mines a block rather quickly. So our adjust difficulty function lowers the difficulty of this new block by 1. With the lowered difficulty, the hash of the first block won't look for 3 leading zeros like our difficulty constant would expect, but only 2, since that would represent the newly calculated difficulty. So to fix this test, rather than using the hard-coded difficulty that is static, we're going to use block.difficulty in order to verify that it matches its own difficulty for its hash. So as we save this, once again, we get a complete passing suite for our entire block.test.js file. We can also get rid of this extra toString function that is console logging, so this looks a little more clean. And likewise, if we're not using the difficulty constant anymore, we can also get rid of that. So let's take out the requirement of the config file. Great. Okay, so we know for sure that it lowers the difficulty for slowly mined blocks. Let's add the other test that says it raises the difficulty for quickly mined blocks. And then we have our callback arrow function. For the body of the function itself, it'll look very similar to our previous test, so you can copy that if you want and paste it in. And we're going to expect that if we call block.adjust difficulty with the current block and block.timestamp plus 1, so a block that was very quickly mined after the previous block, well, we'll expect that the difficulty is raised 1, so rather than block.difficulty minus 1, we'll do block.difficulty plus 1. As we save this, notice in the command line now that our new test is passing. Cool. So our adjust difficulty tests are passing, and we know that it raises the difficulty for quickly mined blocks and it lowers that for slowly mined blocks. As an additional test, to truly see this adjusting difficulty mechanism in action and the proof of work system, and all of our blockchain functionality for that matter thus far, let's create a test to explore these features in our dev.test, or rather our dev-test file. All right, let's head to dev-test.js. And in this file, we'll write a test that adds 10 blocks to our blockchain. With our proof of work system in place, this should take a good chunk of time to execute, hopefully around 2 to 3 seconds if our system is working properly, according to the mine rate, which is 3,000 seconds. So first up, let's delete this entire file and start from scratch. And then, first off, we're going to want to access the blockchain so that way we can make an instance for us to work with. Alright, require the blockchain module and set it equal to a blockchain constant. And then let's make our new instance called BC set equal to a new blockchain instance of this class we just imported. And now we'll write a for loop that loops 10 times in order to add 10 blocks to this chain. So let's use for let I equals 0, I is less than 10, and I plus plus. And this will run a loop that goes 10 times. And within the body of this loop, we'll call bc.addBlock. And then how about a template string that says foo, and then let's insert in our numbers. So it'll say foo0, foo1, foo2, all the way up to foo9. And then let's console.log this, so that way we can see what it looks like. And then before we console.log it, let's get the result in call toString. So overall, we have console.log bc.addBlock, and then a template string with backticks, foo, $i, and then toString. All right, this should add 10 blocks to the chain. Let's now run this script with our npm run dev test script that we already have for our application. So back in the command line, we can quit the Jest runner. So let's go ahead and clear this. And then this time, let's run npm run dev-test. All right, as it's going, what we find are that new blocks are created every 2 to 3 seconds or so. So some come in faster than others since their difficulties will be lower, or they're a little luckier than others in finding a good nonce value to generate a passing hash. Also, this whole process itself ideally should have taken around 20 to 30 seconds since our blockchain difficulty was set to 3,000 milliseconds and we generated 10 blocks. So if every block is taking around 3 seconds, the total is 3 times 10, around 30 seconds. Now, you'll probably find that the script finishes short of that 30-second goal. The reason is that this proof of work algorithm is still rather solvable at such a low difficulty. The efficiency of the algorithm in terms of slowing down a miner becomes much more accurate and efficient once the difficulty is raised much higher, and the mine rate is also higher, something on the scale of Bitcoin, for example. For the purposes of keeping this clip watchable though, I won't demonstrate what the system does when the difficulty is set to even a value like 6, since that takes quite some time in order to solve the proof of work algorithm when the difficulty is so high. Plus, it gets more difficult once the mine rate is set to something like 600,000 milliseconds, which is the 10-minute interval that Bitcoin uses. If you like, you can try these high values yourself. It's fun, although you do need to be patient. All right, we've completed the proof of work system with this demonstration in place and our completed tests. With this, overall, we can deter attackers from replacing the blockchain with a corrupt chain in their favor, since it will take a lot of computational power. All right, let's move on.